Are there any questions about anything? So the results of the vote on the scheduling of the second exam look pretty overwhelmingly in favor of doing it Tuesday rather than tomorrow and Saturday morning. So we'll plan on doing that. I'll send an email out to everybody confirming that at some point this evening. So plan on the thing becoming available early Tuesday morning and being available till, basically midnight or whatever on Tuesday. So uh, we'll get that done and that'll fill in that slot in the spreadsheet for us. And tomorrow we turn in our third and final project. There's one last homework. I believe it's due next Wednesday. So everything is kind of getting wrapped up here, getting all the cards on the table. So the material in the book that we have left to cover is basically chapter 9. So we skip over to chapter 9 and do the virtual memory chapter. That's all we'll have time for this term. But this is a really essential, crucial concept for you to understand, to have any kind of idea at all of what actually is going on on the computer as it's running all day long and how things actually work on the computer. This is an essential concept that you have to understand. Um, and it's one of the sort of neater, slicker ideas that we've come up with for how to utilize these computers. So today we want to begin talking about virtual memory and the concepts around virtual memory. And then tomorrow and for the rest of next week, we'll flesh out the details of virtual memory. The stuff we've been talking about with the caches and the cache hierarchy is physical memory at accesses, right? So when the processor actually wants to physically go to get something out of the physical DRAM memory on the computer, that cache hierarchy is sitting there helping it access that in a efficient, fast way, hopefully the degree to which the thing is exhibiting temporal and spatial locality is able to make that cache effective at speeding things up for us. And so we looked at how that physical cache works. But when processes execute, user level processes execute on the computer, they're actually generating virtual addresses. And the virtual addresses are mapped to an actual physical address. And then that physical address is presented to the cache hierarchy and the memory that we've been looking at. So we need to go and look at the step of, well, okay, well, how do we get from the virtual address to the physical address to go place it onto the cache hierarchy? So that's what we're talking about for the next week is the virtual memory. The virtual memory solves a whole bunch of problems for us with one solution. So we get to kill a lot of birds with one stone here. And so that's one of the interesting, neat things about employing virtual memory on a computer system is that it is a tool that simplifies or solves a lot of different issues we have to deal with. So we'll see that uh, as we go along here. There's a lot of different ways, therefore, of looking at what virtual memory accomplishes in that it solves a bunch of these different issues. So the first method that we'll look at is, we'll look at virtual memory as just another form of caching, and we'll look at virtual memory as a tool for memory management and virtual memory as a way to do memory protection, all those different sorts of issues that get involved with management of the virtual memory. So the basic idea is the what we've been looking at is if the CPU generated a physical address, you just go to that location in physical memory and you pick up the contents of what you're trying to get and you bring it into the CPU. And in fact, there are computers that do it this way and they don't use virtual memory. And that would typically be some sort of embedded computer system, like in a car engine or a control device in a factory or something, where essentially you have, one program that is running on the computer all day long doing, has to do one thing. And there's absolutely no reason to use virtual memory on a system like that. But the normal sort of thing is that we have computers that desktops and laptops and these kind of computers that are running a general purpose operating system like, Windows or Linux with hundreds and maybe even thousands of processes that want to run at the same time on the computer. And in those types of situations, we utilize virtual memory. And we're going to learn that the management of the virtual memory is a joint undertaking. There's some things that happen in hardware and some things that happen by executing code up in the operating system to manage certain things about the virtual memory environment of a process. So it's a joint sort of thing, and we need to learn what happens in hardware and what doesn't happen in hardware. But the basic idea of these kind of computers is that the process generates a virtual address. All these addresses we've been looking at in GDB and looking at in our assembly language and all, those are actually virtual addresses that are generated by the process. And the virtual address is then mapped to a physical address. And we have some hardware called a memory management unit that has some things in it that are helping us do this mapping of the virtual address to a physical address on the computer. So we need to learn how that hardware works and what it does. But the basic idea is the processes can run and generate these virtual addresses, and then we can translate the virtual addresses to a physical address on a computer. So we think about memory as being this big, huge linear array of locations. And we can think of that in both virtual addresses and in physical addresses. So we'll talk about the virtual address space of a process. If we had n bits, little n bits of address, then we could have 2 to the n addresses, right? So that would be the size of our virtual address space. And if we had m, which could be different, physical bits of address space for the physical memory on a computer, then we would have 2 to the m amount of physical memory. So this physical memory is your big 12 gigabytes or 16 gigabytes or whatever you happen to have of the physical DRAM that you have on the computer. But the processes live in virtual address space, and they each process thinks he has his own private virtual address space. That is this humongous thing that's bigger than the actual physical memory you have on the entire computer. So each process thinks it has this big monster virtual address space, which is way, way bigger than all the memory on the entire computer. So how the heck is that going to work, right? So the basic idea is that um, the DRAM that's in the computer is going to be used as sort of a cache. Once again, the same caching concept that we see to hold slices out of the virtual address space that are currently mapped to slices of physical memory. And we don't have to hold the entire virtual address space for a process. We can't. It's bigger than all the memory we have. We're only going to hold little pieces of it at any given point in time in the actual physical memory on the computer. And so that's the key, right? So this virtual memory concept is going to solve a lot of problems for us. It's going to show us how we can simplify memory management. It's going to isolate the address spaces of processes because each process has its own virtual address space that's then mapped onto the physical address space. So a lot of different issues are going to get solved with this same thing. So the first view of virtual memory is as a tool that's basically another form of cache. Think about the virtual address space of a process and think about a big, huge collection of space out on the disk, out on a disk drive, right? That represented that big amount of virtual memory. Now, there's some caveats here. This isn't exactly the way this really works, but just imagine to get us going that this is what the situation is, right? So suppose we had this big, huge whopper hunk of space out here that represented this virtual address space of some process. And we would slice it into these pieces, and we'll call these pages. And the pages on our real computer are going to be 4K big, 4096 bytes each. And then we could take those pages, those slices of the virtual address space, and we could associate some of them with an actual physical page of 4K in the actual physical memory of the computer. So at any given point in time, the process that's generating these virtual addresses, right, is only using a small subset of his big, huge virtual address space, right? Maybe you're looping in some code here that lives in this page, and you're accessing an array that lives over in this page here, but you're not accessing your entire virtual address space at any point in time, right? You're just accessing little slices of it. So we could arrange for the ones that you need at this point in time to actually be mapped into the physical memory. And that's the whole basic idea. So we're using the physical memory as kind of a cache to hold little pieces out of the virtual address space of the process temporarily in the memory while the process is needing to access them. Questions so far? Okay. So we go back to these statistics and we say, okay, DRAM is 10 to 100 times slower than the SRAM. And that, we saw that effect happening when we went from the L1, L2, L3 and down to the DRAM and those different speeds and things. And there was a penalty, this big cliff that you got to at the L3 cache where you jumped over into the DRAM and it was way slower, right? Well, now if we're using slices of the DRAM as pages to hold slices out of the virtual address space of a process, which would be stored out on the disk is about 10,000 times slower than the DRAM. So that is a bigger cliff you got to jump off, right? Going from the DRAM speeds to, oh, I got to go and drag it in off the disk and put it in the DRAM. There's this huge penalty that lives there, right? So if you're thinking of the virtual memory as being kind of cached up in the DRAM, then that penalty for going out to the disk is huge compared to the one that we incurred in our physical cache hierarchy. So the consequences of that are we're going to move in things in a big chunk, in our case 4K, being flipped in and out of memory, right, onto what we'll later refer to as the page file on the computer, which is kind of a misnomer. We'll discuss that later. So we need a big mapping function that can map from slices out of the virtual address space onto these pages in physical memory. And if you thought of it as a cache, it would be a fully associative cache because it makes absolutely no difference if I take some slice out of a process's virtual address space. It doesn't make any difference which page of physical memory I put it in, right? So it's completely associative from that point of view if you're thinking of it as a cache of the stuff that's on the disk there, right? And it's also the case that it would be a write back as opposed to a write through style cache, because I'm not going to write anything from the memory back out to the disk and incur this 10,000 times slow penalty, right? Unless I absolutely have to. So I'm not going to do any write through kind of stuff where you constantly are pushing things down to the lower level of the cache. So thinking of the DRAM as being used as a cache for slices of the virtual address space of a process, you would characterize it as a completely set associative, not two-way, three-way, four-way, whatever, right? It doesn't make any difference which page I put it in, right? It's completely set associative, and it's a write back style of cache. I don't initiate any disk writes until they absolutely have to, right? So we're going to have a translation of the virtual address to the physical address. And in order to do that, we'll eventually see that there's some hardware helping us do this. But for right now, let's just think of a big thing called a page table. And so here's the virtual address space of a process. Think of that as a big monster hunk of disk space. That's not really exactly true, but don't worry about it for right now. Just conceive of it as a big hunk of space out on the disk with one slot for every page of the virtual address space. And think of this page table as just a table that says, well, when you access some virtual page, here's the pointer that says what physical page it's currently sitting in. And only a small subset of all of these virtual pages need to be mapped at any given point in time. The ones that are currently being used actively by the process would be the ones that we would have mapped into the physical memory. And that collection that the process needs to use to run right now is called the working set of the process, right? And you'll see this working set thing show up in your operating systems class, because the operating system is going to manage how big that working set is for a given process and the contents of it to a certain extent in terms of what to replace in it. So we have a table, and where does this page table live? Well, it would live in memory in the DRAM somewhere, right? And we'd take our virtual reference and we'd go into this table and say, okay, this is the physical page, and we go make the physical reference into memory. Does that make sense? So let's look at an example of what's going on here. Just like any other cache, you could have hits and misses, right? So if I generate a virtual address that's currently mapped to some physical page, then I hit, right? And I can access it. But if I generate an address for this slice of the virtual address space, it isn't currently mapped to any physical page in memory, and that's called a page fault. So the page that I'm after, the contents of the page that I'm after out of the virtual address space, lives out here on the disk. And so I got to go get it and dump it into memory somewhere and then change this pointer in this table to point to where I put it in memory. Questions about that? So I have to service the page fault. Well, who does that? Well, the operating system does that, right? This page fault is going to cause an interrupt to vector up into the operating system code. The operating system is going to go, oh, this process was trying to access this page and it's not in memory. So I got to initiate some disk IO operations to go get this thing off the disk, dump it into memory somewhere. And then I got to modify the contents of this table, make it point to where I put the thing. And then I restart the process with the same instruction that generated the page fault. And this time it'll work because the thing is mapped into memory. So there's some management of the page table and dragging the thing in off the disk that would have to be done by the operating system, right? So handling the page fault, right, causes an exception to vector up into the operating system. And then you would go get the page, the virtual page 4 is sitting here. And now we're only going to allow you to have 4 total pages of physical memory for your whole process at any given point in time, right? So one of them has to go. So we have to select a victim, just like the hardware selected a victim in the blocks in the cache, right, to replace. So now that we vector up in the OS, we get the OS, he gets to select the victim, right? Which one of these is going to go? And then it has to be possibly written out to the disk because we may have modified its content since we brought it in. We call that a dirty page, right? But if it hasn't been modified, we can just chuck it. There's no reason to do a disk IO if you don't have to, right? And just mark in here that he's no longer pointing, this slice of the virtual address space is no longer currently mapped to physical memory. So we'd pick a victim, and then we'd go we evict the victim, and we go get the page we're after, in this case, virtual page 3. And now we show that this entry that used to be pointing to the memory is now pointing out, and he's on the disk, right? And then the one for page 3, the one that caused the fault, we dragged that in, dumped it into the memory, and now we have this pointer pointing to the memory where we put it. So that's the replacement of a page in memory and the management of the page table. And the OS would be doing that when this page fault occurred. We'd vector up into the OS and it would arrange all this stuff to happen. And now if we restart the process that caused the page fault, it'll generate the same virtual address, but now it's mapped to some place in physical memory, so it'll work, right? We can go get it out of the memory of the computer now, right? Any questions about what it may mean by a page fault and who handles it? All right, so we move on. So we restart the offending instruction and we get the hit, right? That's the whole idea. So is this virtual memory going to work? Well, we've got this huge amount of delay that we have to do to go get these things off a disk and dump them into memory and maybe write them back if we dirty them. And now we're throttling the rate at which we can run the computer with this really slow peripheral device and not even the slow DRAM thing, right? So that doesn't sound very good, right? Doesn't sound like it's going to work very good. But the problem is, the solution is locality once again, right? If the process is executing in this working set of pages and it's looping tight in some loop and pounding on some array or whatever, and it only needs for this little burst of time to access addresses in this range of its virtual address space, well, those are all mapped currently to memory, and it can be just perfectly happy getting those things out of memory. So the degree to which locality is exhibited now becomes extremely important again, of staying within your working set and not just jumping all over your virtual address space. Making the thing flip things in and out off the disk would make it run really, really, really slow, right? 1,000 times slower. That's really, really, really slower, right? So this working set concept is another instance of the principle of locality, temporal and spatial locality exhibited by the process as it executes. Only now the locality that we're talking about is locality of virtual addresses in the range of the virtual address space. To what degree do I concentrate in on a very small subset of those virtual addresses and just keep generating them? And if I got those mapped into physical memory, things are going to go good for me. So that's this idea of a working set, right? Now, if you had each process on the computer thinks it has its own virtual address space that goes from 0 to however many bits you have in the address, right? Thinks it has this humongous virtual address space. And if I have 500 processes running on the computer, and each of them thinks they have that huge virtual address space, each of which is way bigger than all the physical memory I have on the entire computer, then you see that you're going to need a lot of locality to have what you need in the memory of the computer to make it run effectively. And if the sum of all the working sets of all the processes running on the computer was way bigger than the amount of physical memory that I had, then I'd have to start flipping things in and out a lot off to the disk, and things would get really nasty. So as you're going to see the way we manage this stuff and the way it behaves, we don't really have to end up flipping things in and out a whole lot off the disk, which is the key. And the key is really based upon, once again, the fact that these things exhibit locality of reference. So there's different ways of looking at virtual memory and what it is. The way we just looked at it was as a way of caching a huge virtual address space into a little small collection of pages in physical memory and flipping them in and out, making it behave like another form of cache, right? Another perfectly equally valid way of thinking of virtual memory would be as a tool management from the point of view of the operating system. The operating system has to get some memory for a process to live in to execute, right? And so here's a process, process one, here's another process, each of which thinks it has this humongous virtual address space. So here's virtual page one from this process, virtual page two from the same process, and they can map anywhere you want to put them into the physical memory. And then this other process, they can put anywhere you want to put them in the virtual memory, in the physical memory, right? One of the interesting things you see here is that we could make entries in the page tables for the two different processes point to the same physical page if we wanted to. And we do that for implementing library code. If I have 1,000 processes running on the computer and every one of them wants to run the code in the printf function, well, I don't need to have 1,000 copies of the printf code, right? I could have one copy of it sitting in memory, and I could arrange for all of these different processes to point to that same copy of it, and they could run the code that was living in there. And we do that through what are called dynamic link libraries in the Windows world. In the Unix world, we call them shared objects, SO files. But in any event, this is another way you can view virtual memory as solving this kind of problem for us, as managing the memory from one process's address space and the memory from another process's address space. And we want to keep these things separate in the normal case, right? So they just point off to different pages in memory. And so this process can't stomp on the address space of the other process, which is what you want, right? But if we wanted to, we could make them share things. So we solves a lot of different problems for us, right? We can share code and data amongst processes by putting those things in like that, right? From the point of view of the operating system, your process looks like this, right? You have this big, huge virtual address space that goes from 0 to however many bits you have in the virtual address space, right? And the operating system thinks of the contents of your process as a collection of these segments. And you've seen these segments showing up when you looked at the assembly language code. You might have seen .data, .bss, those kind of things in your assembly language code. And so from the point of view of the linker, when it's building your image for your code down here, the text, right? It's grabbing chunks of code and putting them all together into this text segment. And that's the Unix term that we use for the executable code. It's the text segment, like the computer's reading that text. That's what the computer does. It executes the instructions that are in there, right? So then there's a little init code that runs when the process first starts, which is not your main in your C program. The main is actually called from the init code after the init code does some things. And then we could have a section of read-only data, right? Which is another thing we're going to be able to do with this virtual memory stuff. It's going to solve another problem for us about what are the permissions for some process associated with this chunk of address space. Can it only read things out of there, or can it write things into it? And then we're going to have a way on the Intel processors where we're going to be able to control whether you can execute instructions out of a given chunk of memory or not, right? So the permissions is another aspect of this memory management stuff that's all wound up in the solved for us through this one common technique, virtual address space. So then we have other segments that we think of your process as having, right? Like the place for your data to live. And this thing BSS, there's a lot of mythology about, well, what is it? What does BSS stand for? And it pretty much agreed upon, it stands for block with starting string. It's just a leftover thing from evolution in the Unix world. But basically what you have here is you have data that's either a hunk of memory that contains data that's initialized, or a hunk of memory that contains data that's not initialized. And you have different flavors, right? A segment for each. So you'd have your data segment for initialized data and your BSS segment for just zeroed out memory that doesn't really have any initial data in it. That's where that segment of your, and these are just slices out of your virtual address space, right? And then we're going to have the heap, which we haven't talked about, where we dynamically get storage. And it's going to grow in this direction. And then your stack, which we've been looking at, is going to grow in these high addresses down to low addresses on the Intel computer, right? And we put those pointing at each other because in old days before we had virtual memory and you had to find some actual physical real memory to dump this process in for it to live, we would allocate a hunk of space and the stack would grow that way and the heap would grow toward it, and you could kind of get multiple benefit out of the space in the middle. If the heap grew and then shrunk and then the stack could grow and shrink, you could, get a lot of use out of the stuff in the middle. You could reuse it, and you were trying to shoehorn things in those days. You didn't have much memory before the virtual memory thing. So we made them grow at each other. And then when we went to the virtual stuff, we just retain the same thing, even though we have gobs of space now with these virtual address spaces. We still make the stack grow toward the heap. And if they bang into each other, then that's a bad thing. And we check for that and terminate the program. But then when these shared library things came along, we had to have a place to map them into the address space. And so they stuck them in the middle, in between the direction of the heap and the stack. And so it's, you're not getting that same two things could occupy the same addresses at different times in the program effect anymore. But, we had to do it because we had to have a place for these guys to live, right? So that's where they put them. Another thing you see from this slide is this pink stuff up here, and it says kernel virtual memory. What in the world does that mean? Well, this is a thing that might not be obvious to you, but it's crucial that you understand this to understand how things actually work on the computer. And as you get into 347 and 447 and start learning about the operating system, you'll learn more about this aspect of how things work. But we take the virtual address space, and in most cases, we just slice it in half. And the lower addresses is where your normal sort of user process addresses are running in your virtual address space. And the top half of your virtual address space, we map to the operating system. So when we make a request, we run some code to make a supervisory call in SVC. request the operating system to do something for us, that manifests itself physically on the computer as a software interrupt, which vectors up into the operating system code. And when you do that vector into the OS, the CPU flips into kernel mode from user mode. The CPU has, in the case of the Intel processor, 4 modes, only 2 of which we use in the Unix world. But you're flipping from user mode up into the kernel mode. And in kernel mode, you can execute all of the instructions on the computer. In user mode, you have a restricted instruction set. You can't execute instructions, in other words, that would do things like access a port address to go to some peripheral and configure the peripheral, or change some control registers up in the CPU that control the general way that the computer in general operates, right? So there's all these restricted instructions that don't execute in user mode when the user process is running. And when we make a request to the operating system, we vector up through that software interrupt vector up into the OS, and it fields the request that we're making, a supervisory call that we're making, does some service for us. Well, the way that actually physically is manifested on the computer is we just take the virtual address space of every process on the computer and map the top half of it to the exact same places. That is where the OS is laying up there in the memory. So that hopefully, will become clear to you later. But to really understand how the computer actually works, and another trick that we pull with this virtual memory stuff, you have to understand how we get from the user mode up into the kernel mode and how that relates to mapping your virtual addresses. So that may take a while to settle into your head, but to really understand how the computer works, you're going to have to understand that at some point. Okay. Any questions about it so far? Okay. So another way is a way to implement memory protection. And so we can have these bits associated with these entries in the page tables, right? That tell what the permissions are that this process has for that physical page of memory. And so we could have read, write, and supervisor. So what this is saying is, for example, the first one up here, virtual page 0 mapped to physical page 6, that says this process 1, can execute instructions that read out of that memory, but if it tries to write into that memory, it'll cause a segmentation violation, which will vector up into the OS once again. And that would be a seg fault, right? You're writing into a page that you only have permission to read. And so if we were doing that example, like with the printf function, 2 copies of it laying in memory, you wouldn't want the process to be able to modify the code for the printf function, right? So you'd mark both of them's pages as read only, no write, right? So it's another aspect of this whole virtual memory management stuff that we're going to be able to do to solve this problem as well, the permissions associated with pages of memory, right? So we'll have these bits that, that are entries in the page table, and we'll see how those bits get physically implemented in the hardware by the CPU as it's making those accesses to memory. So the other bit that's shown here is supervisor. Do you have to be in kernel mode to access this page? So that would be like all those pages out of your virtual address space that map up into the OS. You can't even read those when you're in user mode, right? You have to have the processor flipped into kernel mode by making that software interrupt up to make the OS service request, right? Before the page could even be read. You don't want the user process to be able to read passwords or whatever they're laying in the memory of the operating system, right? So those pages could be marked with this bit flipped on, which says if the process is executing in user mode and does anything to try to touch that page, that's going to cause a fault. It's going to cause an exception, vector up into the OS and kick the thing out of the computer, right? Does that make sense? So that's another aspect of this virtual memory management thing, is going to be able to put these permission bits. So that way, virtual memory is solving that problem for us as a tool to provide some sort of scheme for memory protection, right? So it's all wrapped up in one solution to a lot of problems. Questions about this stuff so far? Now, I know the first time you look at this, it's kind of hard to get your head around a lot of it, but keep at it and rigorously read through chapter 9 in the book, because if you don't understand how virtual memory works on the computer and how we use it to solve these problems and how we use it to interact with the operating system, then you really don't have any clue as to how the computer actually really works, right? So to really understand how the computer works, you've got to climb this hill. You've got to get this concept down in your head about what is actually going on when your processes are executing and generating these virtual addresses, and how they're being mapped onto physical addresses, and how these page tables are being managed, and what's going on in hardware and what's going on in software. So to really understand the operation of the modern computer, this is a fundamental concept that you have to master in order to really have any clue at all as to how a computer actually works. Okay. And this will keep coming up to understand what goes on in 347 and 447 when you start studying the operating system, how it's doing its job. You need to understand the hardware for the virtual memory translation schemes that we're going to discuss. So you see how the operating system is interacting with that to do its job. Questions so far? Okay. Well, so this point is, going through all these slides, there's a lot of different ways you could look at what does virtual memory accomplish for us. You could look at it as another form of caching. You could look at it as another form of, as a way to do memory management. You could look at it as a way to do memory protection. Truth is, it is a way that one thing can solve all those problems for us, right? So the fundamental thing that has to happen ultimately is, when a process is running and it generates a virtual address, that virtual address has to get mapped to a physical address to then actually grab the stuff out of memory, right? So we're going to have to go through and see, how does this translation happen? And there are going to be parts of it that happen by the hardware, right, doing the translations. And then there's going to be that page fault thing that we mentioned, where we vector up into the operating system to manage the contents of the page tables, to manage the working set of the process, right? And so there's different aspects going on here. There's the hardware doing translations, and then there's these cases that come up via the page fault where the OS has to get involved. So it's a joint sort of thing going on between the software, the OS, and the hardware. So you need to learn what happens in each piece, right? The general rules or nomenclature we're going to use is, a virtual address space is some big, huge, contiguous collection of bytes that we think of. And that is different from the actual physical address space on the computer. The physical address space is your DRAM, right? That 12 gigabytes or 16 gigabytes or whatever the heck you have, that you think of the physical memory that's in the computer. Every process thinks he has his own virtual address space, which starts from 0 and goes to however many bits are in a virtual address, right? And that's huge. It's much bigger for that one process than all the physical memory you have on the entire computer. And every process thinks it has that huge virtual address space. And I have hundreds or thousands of processes running on the computer. So the translation is going to be simply a mapping function, if you want to think of it abstractly, mathematically, where we take a virtual address, right? And we map it to a physical address, union the null set, because maybe it isn't mapped to any particular physical address at this point in time, right? So for any virtual address A, mapping that virtual address to some corresponding A prime, if the data at virtual address is at some physical address A prime, then this mapping function would map it to some physical address. But if it isn't mapped to some physical address currently, it would be the null set. The virtual address is not in physical memory. And that's two subcases. Either the reference to this virtual address A is an invalid reference, meaning it's not even currently part of your active virtual address space, or it is currently part of your virtual address space, but it's just not currently stored on in the memory. It's stored out on the disk, which is that page fault case. So this one has two subcases. One of them is the seg fault, the segmentation fault, and the other is the page fault, right? The page fault will get fixed for you by the operating system. The seg fault will cause the operating system to kill your process, right? So we want to learn how this translation happens and what hardware gets used to help us do that and how these page tables work. And so this is going to be an involved process of peeling back a lot of different things to get down to the details of how this actually functions on the computer. But it's essential that you understand this to have a conception of how the computer actually is working and doing what it does. Okay, so any questions about this so far? Questions about anything? So we will continue on here tomorrow. So please read in chapter 9 before you come to class so you can know what to ask from things that maybe didn't gel in your head right when you were reading in the chapter. And we will flesh out how this virtual memory stuff actually works. It's a really neat, clever trick, and it enables us to have all of these gazillions of processes in the computer at the same time, each of which thinks it has a huge virtual address space that it lives in. And in reality, at any given point in time, they only have a little teeny amount of memory that's physically allocated to them that they're running in, right? Does that make sense? So, how does that actually work? So, any questions? Well, we got a project to do tomorrow. Your last homework is due next Wednesday, and our second exam takes place next Tuesday. So we will have filled in most all of the slots in the spreadsheet by that point in time. The only thing left would be the final. So all the cards are getting put on the table and final scores are shaping up. There's a question about passwords for Zoom. currently we only have one password that you need. I emailed it out to you, and that is if you want to access the Monday, Thursday, Friday lab sessions, there's a password associated with that Zoom session. But right now, we don't have any other passwords that we're messing with, and we only have 1 week left to go in the term, so I don't see any point in complicating things and throwing a monkey wrench into everything right here at the last minute. So we don't have any passwords except for that one case. The office hour sessions for Monday, Thursday, and Friday have a password. Okay. So you don't need a password to get into the classes here. Okay. So read chapter 9. It's essential that you get to where you understand this virtual memory stuff, and we'll explain it more tomorrow and next week and get you where you see how it's all working. But this is essential information to have any kind of clue as to what's really going on the computer. So office hours are at 2 today. I have a faculty meeting at 1. Hopefully I won't be late getting to the office hours, but if I'm a few minutes late, it's because the faculty meetings usually tend to run over until everybody starts complaining. So I'll see you at office hours, or I'll see you in class tomorrow morning. Have a great day.